In this video, I will discuss the JEE Advanced PYQ from the topic Simple Harmonic Motion. First, I'll give some basic ideas. Consider this spring block system. It's on a horizontal surface, spring constant K, and mass of the block is M. So this is the natural length of the spring. So from this relaxed position, if you give a displacement of x towards right, the spring is getting stretched. So it'll try to come back, and the force that's acting on this block will be F equal to K into x, where K is the spring constant. Now suppose if I compress this spring by pushing the mass towards the spring, then the compressed spring will try to push it back towards the mean position with a force K into x. So the direction of force is always towards the mean position. So this is a normal spring, but now I have a special spring which behaves like this. Block of mass m, and there is a spring fixed at one end, and the whole thing is lying on a horizontal surface. Now this spring, if I try to give a displacement towards right, the spring will get stretched and it pulls it back towards the mean position with a force F equal to Kx. Now if I try to compress the spring by pushing the block towards left, we'll try to push it back with a force Kx. But the property of the spring is it pushes a different force. So when it's pushing, the spring constant is K2. When the stretched spring is pulling it back, then the spring constant is K1. So this is a special type of spring which behaves differently when it is stretched and when it is compressed. So this system, if I pull the block to a distance and leave it and start oscillating, so the oscillations will look like this. It will be symmetric about the mean position. It will reach an amplitude A on this side and A on the left side. Now what will happen to this system? I try to stretch this mass by an amount and then leave it. It will start oscillating. But since the spring constant is different, it won't be symmetric like this. Suppose I take the case where K1 is less than K2. Then the oscillation will look like this. It won't be symmetric. So the amplitude for the first half, it will be A1, and for the second half, when the spring is getting compressed, it will be A2. And this time from here to here, it's T1, and the time from here to here, it's T2. The vertical axis is the time axis. This is x displacement. Similarly, here is the time axis, but here it's symmetric. So the time from here to here is T by 2, and the time from here to here is okay. So we can get T1 and T2 once the system is known. So here in normal spring, we have this relation for SHM, K equal to M omega square. If this relation is valid, then we have SHM, where K is the spring constant, M is the mass of the block. So since the system is known, K and M are known, from this I'll get omega. Once omega is known, I can find the time period of oscillation as 2 pi by omega. But in this case, in the first half, where the spring is getting stretched, the same addition is valid, but we have K1 equal to m omega 1 square. Okay, and similarly for the second half, where the spring is getting compressed, I have same K equal to m omega square, but K will be different from the first half, and omega will be different. The spring is known, so K1 and K2 are known. From this, I'll get omega 1 and omega 2. Okay, so from omega 1, I get T1 for the corresponding time period T as 2 pi by omega, or 2 pi by omega 1, or if you call this as T1, this is actually half the time period, so it's T1 by 2, this is T2 by 2. Okay, so K1 is known, M is known, so I'll get omega 1. Once I know omega 1, I know T1. Similarly, I can find T2 as 2 pi by omega 2. Since K2 is known, I can find omega 2 from the T2. So from this, I get the time period of this oscillation T as first half time period T1 by 2 plus second half time is T2 by 2. So this one is the symmetric oscillation. We'll keep on repeating. Here it is asymmetric. It's not symmetric. First half will be different from the second half. If K1 is less, means A1 will be more. And if K2 is more, means A2 will be less. And even T1 and T2 will be, since K1 is less, omega 1 is less, so T1 is more. So we also have T1 greater than T2. T2 is more, so omega 2 is more, so T2 is less. K2 is more means this spring is tight spring. Means I need larger force to compress it. K1 is small, it means it's a loose spring. This spring behaves same both while stretching and compressing, but here, while stretching it's relatively loose, while compressing it's a little bit tighter. So loose spring means will go amplitude will be more, and also time period will be more, or the corresponding half time period. Tight spring means the amplitude will be smaller, and the half time period will be also shorter. So with this understanding, you can solve this JEE advanced question. This is a question. On a frictionless horizontal plane, a bob of mass m equal to 0.1 kg is attached to a spring with natural length L0 equal to 0.1 meter. The spring constant is K1 equal to 0.009 Newton per meter when the length of the spring is L greater than L0, and K2 equal to 0.016 Newton per meter when length is less than L0. Initially, the bob is released from L equal to 0.15 meter. Assume that Hooke's law remains valid throughout the motion. If the time period of full oscillation is t equal to n pi seconds, then the integer closest to n is dash. You can pause and run this question. Here is the solution. So there is a bob of mass n, 0.1 kg. It's attached to a spring. And this is fixed at one end. So this is a special spring. When L is greater than L0, that's means stretched. Spring constant is K1. L less than L0. L0 is a natural length, initial position. The spring constant is K2. Initial length L0 is 0.1 meter, and initially the bob is at rest at 0.15 meter. So the bob is stretched by an arm towards right, and then it's left. So for the first half, T1 by 2 is, we got that relation. For an system, we have this K equal to m omega square, and time period T is 2 pi by omega. So time period is 2 pi into 1 by omega, that's m by K square root. Okay, so the first half, the duration will be half the time period, which is pi into square root of m by K1. The spring has the swing constant K1 when it is getting stretched. Initial position is 0.15 meter and the natural length is 0.1 meter. So initially it's in a stretched position. So the first half will be a stretched motion. And one half of the motion will be compressed motion. So that will be the time period corresponding to pi into root of m by K2. Spring behaves differently when it's stretched and compressed. So this time period T is sum of these two, pi into square root of m by K1 square root of m by K2. Time period is n pi seconds. So we have to, this is actually n. So we have to find this value and get the closest integer to it. M is 0.1, K1 is 0.009, square root, K2 so this is 1 by square root of 0.09 plus 1 by square root of 0.16. These are perfect squares. It's 0.3 square, that is 0.4 square. So the time period T is pi times 0.3 into 0.3 is 0.09. So 1 by 0.3 plus 0.4 into 0.4 is 0.16. So this is 0.7 by 0.12. That is 70 by 12, which is 72 minus 2 by 12. So 6 minus 2 by 12, 6 minus 1 by 6. So this is the value of n. So the closest integer, so n is approximately 6. Time period of full oscillation is n pi seconds. We have to find n and the closest integer to it. So closest integer is 6. 6 is the correct answer. So here, when the spring is stretched, that is length is greater than L0, spring constant is K1. And when it is compressed, spring constant is K2. So time period of oscillation is half, first half time and the second half time. So time period is 2 pi into square root of m by k, but since half the time, it's 2 is gone, just pi into square root of m by k. So to simplify this one, so you'll get 5.83, which is approximately 6. So answer is 6.